Welcome back, everyone. In the last lecture, I talked to you about the evolution of the eye and some things that we can learn from that process that tells us about the evolution of novelty. And one of the things that came up in that lecture is that the evolution of complex characters often involves reassembly of existing components in new ways, and that we can think about evolution as repurposing and tinkering with the traits that already exist in organisms. So this lecture zooms in on that a little bit and explores this idea of evolution as a tinkerer. We can use the eye actually to explore some of the consequences of evolution as a tinkerer. And these consequences apply to the eye, but they also apply to other complicated morphological structures that have evolved through this process of co-option and reuse and recombination of parts. Okay, so what I want you to do right now is an experiment. And this experiment uses this slide right here that has the letters R and L on it. And what I want you to do is to choose one eye and close the other eye. So maybe you want to choose your right eye, so you close the left eye. And then focus on the appropriate letter, R for right and L for left. Place your eye at a distance from the screen approximately equal to 3 times the distance between the R and the L. Move your eye slowly towards or away from the screen until you notice the other letter disappear. For example, close your right eye, look at the L with your left eye, and the R will disappear, vice versa. So try that and see if you can get it to work. Hopefully you're having the experience that I had when I did this, which is amazed and confused. So the reason why we have this phenomenon where there's a part of our vision that's actually missing and it's just being filled in by our brain is that our eye has a structure called the blind spot. And you can see kind of a conceptual diagram of the eyes that we have, and here's the blind spot. The blind spot actually is where the optic nerve comes through the retina to connect with all of the rods and the cones in our eye. And the reason why we have to have this blind spot is because actually all of our light sensing structures in our eye and our retinas are upside down. And so their connection to the nervous system comes out through the top of the retina and then has to go back through the retina to get to the path to the brain. So because of that, we have a blind spot. Our brain is really good at deceiving us so that we don't realize that we have this blind spot, but we do. So when you're looking around, there is that area where you actually are not getting any information about what's in the environment for both of your eyes. And this blind spot in the eye is a great example of what happens when you have a trait that is built by a tinkerer rather than an engineer. No engineer would install a retina upside down and then just drill a hole through it to cable it to the brain, and yet that is the structure that we have in our eyes, and it works out just fine. Another example of what happens when you tinker instead of building something from scratch, we can see when we look at the structure of our ears. So for the ears, you might think of the problem as designing an organ that can hear sounds well in terrestrial habitats. And you might be able to do that by assembling some parts that you could build from scratch, but evolution doesn't do that. It tinkers with what's already there. And so that result of that tinkering is that we have these series of bones that early on in the evolutionary origins of mammals were large components of the jaw, but through evolutionary history became smaller and smaller and moved until now those bones make up the tiny bones that are inside our ear, critical for our hearing and completely separate from the jaw. These ear bones are a great example of an exaptation. This is a term that you should know for this class. An exaptation is a character that evolved for one function, for example, to help the jaw move in a jointed way, but was co-opted during the course of evolution to serve another purpose, in this case, hearing. Another good example of an exaptation is feathers. And so here so lots of fossil findings lately have shown that many dinosaurs had feathers. And the idea for something like this Eutrianus is that the feathers were there for thermoregulation. Obviously, this is not a flying animal. So feathers are great for thermoregulation. They can keep you warm in cool environments. But it turns out that later on, we could co-opt those feathers to allow some of the dinosaurs to fly. So let's just take 3 general principles of the tinkerer and its consequences for trait evolution. One is that tinkerers, so evolution as a tinkerer means that we will often see organisms use the materials that they already have but recombine them in clever ways. And a good example of this is these three bones in the human middle ear that all originated as large elements of the jaw. The second principle of the tinkerer is don't plan for long-term goals, just adjust when needed. And a good example of that is feathers. So feathers were great for thermoregulation, but it turns out that they're good for flight and also good if you're going to insulate yourself swimming around in water like a penguin. And three, tinkerers create projects that have a deep imprint of their history. They show their history, and we can see that in the evolution of the eye with our retina and blind spot. Interestingly, another organism, the octopus, has an eye quite similar to ours in many ways. This is all convergently evolved, but their retina is right side up, and so they have an optic nerve passing from behind towards the brain, and so no blind spot. And that reflects a difference in the history of the evolution of the structure in that lineage. So hopefully that gives you a general idea of some of the consequences and the idea of evolution as a tinkerer. Thank you.